students, welcome back. This is Torres, elbow bump. How are you? Are you doing okay? How's your family? Are they okay? Remember, if you need anything, send me an email so that I can try to help in some way or another. So lucky you, you get to hear my voice for another lecture. But the best part is we're going to be estimating population proportions with confidence intervals. Yay! In our last lecture, we used the distribution of sampling proportions to estimate the probability of an event. Let's do a quick example just to do a little refresher. So this one is about pets, and it says Pet World has 1,000 customers, of which 25% own cats. A random and independent sample of 100 people is taken. Question: what is the approximate probability that the proportion in our sample will be more than 29%? Greater than 29%. Okay, begin by checking conditions for the central limit theorem, and it tells us which ones. We want to find the standard error. It wants us to calculate the z-score, and it wants us to find that probability of that it will be more than 29%. All right, we can do this. Okay, so I'm going to go ahead and go into my Zite Board. Remember that Zite Board is always in the description box below. Okay, so what I've done here is I've just pasted that same question into our Zite Board. And let's see what I have. They're telling us the population is 1,000 people. So big N is 1,000 because that's the population. That's all the customers that Pet World has. And they're saying that the population proportion is 25%. And I'm going to go ahead and write that as a proportion, as a decimal. They take a random and independent sample of 100 people. So our little n is 100. Okay, so let's start by checking the conditions of the central limit theorem, because it doesn't say anywhere in here that it's a normal distribution. So first one, is it random and independent? And yes, it is. So we're going to say check. Next one is we're going to go ahead and check our sample size. And I need the successes and failures to be greater than or equal to 10. So the first one I'm going to check is my successes. So I want to take the 100 people times 0.25, right? I'm going to take my sample times the proportion, and I'll go ahead and get my calculator out here for you. Just got my Google calculator, and I've got 100 times 0.25, and I'm going to get 25. Yeah. Okay. So here I've got 25. Is 25 greater than or equal to 10? Yep. Check. So these are how many people are cat people. Well, you're either a cat person or you're not. So who's left? 75 other people, right? So I can just do that by subtracting 25 from 100. Yeah, if you want to do it with the formula, we can just take 100 and then 1 whole minus 0.25 and multiply those things together. And I'm going to go here, clear this out. So I've got 100 times parenthesis 1 minus 0.25, and then hit equals, and I get 75. So see, it's the same. It's the same as 100 minus 25 is going to be the 75, because it's just saying everybody else. So is 75 greater than or equal to 10? Yes. It is, so check. All right, so now we have the sample size condition is met. Okay, I'm going to scooch this down a little bit and go back to my black pen. And the last one is the population size. And that means that the population size has to be greater than or equal to 10 times the sample size. Well, the population size is 1,000 and my sample size is 100. So it's saying 1,000 is greater than or equal to 1,000. Is that true? Yep, sure is. So check. So all three conditions of the central limit theorem are check, and so I can assume that the distribution is normal. Okay, so now I'm going to go ahead and I check the conditions of the CLT. Let's see what I've gotten done here. I've checked the conditions of the CLT, did that, and now I've got to find the standard error. Before I do that, I'm going to go ahead and just start drawing this out and draw myself a normal curve here, because I like to have a really clear idea of what I'm working with. So here's my normal curve. The population proportion is 0.25, and I need to get an idea of the width of the standard deviations, right? To see if, to kind of get an idea where 29% would be. So since this is a sample, right, I need to find this distance with my standard error. This distance is going to be my standard error. So I've got my standard error formula, which is the proportion multiplied by 1 whole minus the proportion divided by my sample size. Okay. So let's go ahead and plug this in. I've got SE equals radical 0.25 times 1 minus 0.25 divided by 100. Okay, so now I just need my Google calculator again. Great, I'm going to go ahead and clear it out. So I've got 0.25 times parenthesis 1 minus 0.25 close parenthesis equal divided by 100 equals, and then take the square root of that. Remember, if I click answer, it'll give me that last number that we worked with, and I will get 0.043. Okay, awesome. So I'm going to put that over here, and I'm going to get here 0.04330. Okay, now remember, there's a whole bunch of numbers that are after this. Let me scooch this over again. There's a whole bunch of numbers right here, but it's kind of crazy to draw them out all the way out to here, right? It's just, for me to write this out, it would kind of be really cumbersome. So I'm going to round, but every single time I round, what am I doing? I'm introducing little bits of error, little tiny bits of error, okay? Move this out of the way. Now I know that this distance in through here is approximately 0.04. So 0.04. Okay, so if I add 0.04 this way, and I'm going to just make this a little bit bigger. I'm going to scooch this up and make this a little bit bigger for our eyes. Okay, so this is 0.04. Okay, so this is going to be 0.25 plus 0.04 is going to be 0.29. Another 0.04 is going to be 0.33, and another 0.04 is going to be 0.37. And if I subtract, this is going to be 0.21, and then subtracting again, I'm going to get 0.17, and then subtracting again, I'm going to get 0.13. So what I'm doing is I'm just creating this model so that I have a good idea of what this is going to look like. Okay, so here's my model. And these are my P, but also remember that z-scores correspond with each one of these lines. So the z-score that corresponds with the population proportion is going to be 0. The z-score that corresponds with one standard error above the mean is going to be +1. 2 standard errors above the mean is +2, and 3 standard errors above the mean is +3. In the opposite direction, I'm going to be going 1 standard error below the mean is -1, 2 standard errors below the mean is -2, and 3 standard errors below the mean is -3. So these are just my standardized z-scores. And I want to know approximately what is the z-score that goes with this. Okay, well, it looks like it's going to be 1, or it's going to be very close, but remember we rounded. So what I can do is I can just use my z-score formula that we used to use, and that is just the probability that I'm interested in minus the population proportion divided by the standard error. So what probability am I interested in? I'm interested in 29%. And from that, I'm going to subtract 25. And then I'm going to divide the whole thing by 0.04. Let's just do 33. Okay. Where's my Google calculator? All right. So now I'm going to clear this out. 0.29 minus 0.24. Now you got to hit enter so that the calculator knows that you're done working with the numerator. And now you're going to divide by 0.0433. Hit enter, and I get a z-score of approximately 0.92, positive 0.92. Which makes sense, right? Because this is +1, and this is just a little bit off. Just a little bit off of that. Okay. Anyways. All right. So I've got a z-score that makes sense. It's right around here, just before the +1. Perfect. Now I need to find the probability associated. So we want to know, let me go back to my question. We want to know what is the probability of there being more than 29% of the people in the sample that are cat people. So I want to know everything. I want to know everything from approximately here in this direction. All this stuff. My coloring gets worse and worse and worse and worse, but I can tell you this, it's kind of a little bit relaxing. Okay. Yeah. All right. So there it goes. That's as good as I'm going to color. So basically now I need to know what percentage of the curve is colored red right here. So, okay. So I'm going to go to StatCrunch. Go to StatCrunch. I can go to calculators and then go down to normal. I'm going to put in my population proportion, which was 0.25. My standard deviation was 0.0433. And I want to know how much of it is greater than 29. And I should have that picture that pops up here should be identical to the picture that I drew. That looks about right. So what is the population proportion right here? It says that it's 0.1777. Hopefully I remember that. Okay. So let me scooch this down. So the probability, I'll keep it in red, the probability of the proportion being greater than or equal to 0.29 is 0.1777 or 17.77%. Okay. Another way to say this is the probability of z being greater than or equal to positive 0.92 is 0.1777 or 17.77%. Now, why is this the same? It's the same because this probability, 0.29 lines up with the z-score of 0.92. Here, remember, this is just an estimation that I made just so that I could have a rough estimate, but I had a little bit of an error. I had rounded my standard error. It was less than what it actually was. So I had a little bit of a mistake. I won't call it a mistake because it's not a mistake, it's just error. I'm not being as precise. If I would have used more than just 4 digits after the decimal point, it would have been even more precise. And that's kind of what we're looking for. In our pet world example, we knew the truth. The owners of the store happened to know that 25% of their 1,000 customers were cat people. But the thing is, we often do not have the population parameter, so we cannot be certain of the truth. If you remember from a couple big ideas ago, we talked about introducing error into our statistical testing through a variety of ways. One of the ways that we introduced a little bit of error into our last example was when I rounded the standard error. We just rounded it for the sake of convenience, but I am chipping away at the truth when that happens. So we want to avoid introducing error from the start. That's the plan, but you're never really going to be able to get rid of it, which means that you won't really know if at the end of your calculations you have the true population proportion based on your sample. So in order to deal with that problem, what we can do is we can give an idea with some degree of certainty of where the truth can lie within a sample. And that degree of certainty is called a confidence interval. A confidence interval provides us with a range of plausible values for a population parameter to exist. They'll give you the low end of the range, the high end of the range, and they'll say somewhere in through this range is the true population proportion. We understand that there's some degree of error. We think that the true population proportion is this one that we calculated. We can't be sure because there's error, but we can say with some degree of certainty, either 80% certainty, 85% certainty, 90% certainty, 99% certainty, whatever it is, that the true population proportion lies within this low number and this high number. The confidence level, be it 85%, 99%, 95%, 99.9%, expresses how confident we are that the true population proportion exists within that range. How can we be so confident? Well, the wider the interval width, the more confident we are. Let's look at these numbers right here. Let's just say our population proportion was 50%. We would have a 68% degree of certainty that if we believe the sample proportion is 50, then we can say with some degree of certainty, 68% of degree of certainty, that if it's not 50, it's between 49 and 51. We can also make the interval wider. So we can say within 95% of certainty that the truth exists between 48 and 52. We think it's 50, but we admit that there might be some error in this. So we can say with some degree of certainty that the truth is somewhere between 48% and 52%. We can go even wider, okay? More degree of certainty. But we can have 99.7% certainty that although we believe the true population proportion is 50, we're 99.7% confident that the true population proportion is within 47% and 53%. And we can also say this really wide interval that basically we're almost 100% sure, 99.99% sure, that although we think the population proportion is 50, we're pretty confident it's between 46% and 54%. Really, really, really sure. Notice this 99.99 practically covering up the entire number line. Of course they're going to be that sure because they've covered themselves for almost all the possible values. They become less sure when this width is smaller. There's more of a chance of making a mistake. So where are these random numbers coming from? Well, if you notice, 68, 95, 99, you might have heard those values before. And where have you heard them? You've heard them with this. 68, 95, 99. So while these are common confidence intervals, they could be anything. But basically what they're showing, right, regardless of what it is, what they're showing is what is the z-score that is before and after the mean or the population proportion that would create that interval, right? So if you wanted a 68% confidence interval, you would need this raw score that is aligned with one standard error below the mean, and you would need this raw score which is aligned with one standard error above the mean. Same thing is happening here with 95% confidence interval, which is a very common confidence interval. You would need to know, okay, I think that this is my proportion, but I can say with 95% certainty that if it's not this number, then the true population proportion lies within whatever this raw score is that corresponds with two standard errors below the mean, and this raw score which also corresponds with two standard errors above the mean. One more thing that I want you to notice, let's just take 68%. Notice I have this standard error that is one above the population proportion, and it is symmetrical to the other side, which is one standard error below or less than the population proportion. If I just have half of the interval, this half of the interval is called the margin of error. So two margins of error, one on each side of the population proportion, will make the confidence interval. Now, when we worked with the normal curve, we were doing approximations. And remember, approximations lead to error. So what we're going to be doing now is looking at how to continue to reduce that error, increasing precision. So I'm back on Zite Board, and I have a sample question here about birth control. It says, the Kaiser Health Tracking Poll surveyed 1,504 randomly and independently sampled American adults and asked them if they supported or opposed the requirement that private health insurance plans cover the full cost of birth control. The poll found that 61% of respondents supported this requirement. What percentage of all American adults support this requirement? Calculate the 95% confidence interval level. Okay, so first, this says nothing about this being normally distributed, so we have to check the central limit theorem. So let's check CLT. So number one, random and independent. Check. It says this right here in the question. Number two, we need to see if our sample size is okay. Let's check that now. Okay, so next I need to check for my sample size. All right, so my sample has 1,504 people, and the proportion, the p-hat, was 0.61. And why do I know that this is a p-hat? Well, because they're using a sample. We weren't told the true population proportion. Remember, Cat World, the owners knew how many customers they had. Here, there is no way to know what is happening. They can only go by what the sample says, right? So let me go ahead and pull my calculator over again and clear this out. And let me try to see what I'm doing here. Okay, scooch this. So I've got 1504 multiplied by 0.61 equals, and I get 917.44. Let's just, since these are people, I'm just going to round it up to 917. So is 917 greater than or equal to 10? Yes. And the other way that I can do this is multiply this out, but remember, I can also just subtract that from the poll. So I've got, my number was 1,004 people in the sample, and I'm going to multiply that by 1 minus 0.61, close parenthesis, equal, and I'm going to round that up to 587. This is 1504 times 1 minus 0.61, and that is going to be 587. And is that number greater than or equal to 10? You bet it is. So I'm going to put that in check. I like green checks. I don't know why I did that one in black. Let's just change it to a green check. Check. Okay. Now the last one is population size. I need to make sure that my population size is at least 10 times bigger than my sample size. So population has to be 10 times sample size. Well, population is all Americans. And is that bigger than 10 times 1,504? Oh yeah, because that's only 15,040. So is all the Americans more than 15,040? Oh yeah. So another check. So it meets all the conditions of CLT. Awesome. Let's keep going. Okay. So now I have I know this thing meets the conditions of the central limit theorem. And what does that mean? Well, that means that I can assume normality. And that 0.61 is going to be right there in the center. And I'm working with a sample, so I'm going to have to estimate the standard error for this. And I'm going to need to know what this distance is. So in order to estimate the standard error, I need to find it. It's my little dog sleeping. Okay, so now I've got to plug this in. So here I've got 0.61. You know what? I'm getting sloppy. Let's write this out. My p-hat was 0.61. My n was 1,504. And I'm working with my sample proportion, right? So I'm going to need to estimate the standard error. So I've got 0.61 times 1 minus 0.61 divided by 1,504. Okay. Come here, Google Calculator. And I'm going to scooch this, I'm going to make this a little bit wider so I can get everything in there. Okay, great. So now I've got, to clear this out, I've got 0.61 times parenthesis 1 minus 0.61, close parenthesis, and there's my numerator. Now I'm going to divide that by 1,504. And there is my fraction, and now I'm going to take the square root of that number, and I'm going to get 0.01257. So my estimate of the standard error is 0.01257. Now if you remember, and I'll scooch this over here one more time, I'm rounding this. I didn't put this crazy long number because it's crazy long, and I'm doing this by hand. If I had a computer, I could just keep these things out until however many decimals I want, and it would be fine. But just for the sake of my own sanity, I'm going to keep this number, you know, a little bit small. Not real small, but a little bit. So let's keep drawing my picture. If you hear little squeals, comment down below because that's my dog. So I will give you extra credit if you tell me at what time my dog was squealing. It's available to the first 5 people that hear this message. Okay, so here is 0.01. That's this distance right here. So 0.61 plus 0.01 is 0.62. And then another 0.01 is 0.63. And then another 0.01 is 0.64. And if we go in the opposite direction, one standard error below the expected proportion is 0.60. And one more standard error below is going to be 0.59. And one more standard error below is going to be 0.58. All right, so now I have this all nice and written out. Okay, now let's go up to my question. My question says, what percentage of all American adults support this requirement? Well, that is 0.61, 61%. That's what my sample told me. Calculate the 95% confidence interval. Okay, these are my p-hats. P-hat. And these are my z-scores. What z-score goes exactly in the middle? 0. And then I get +1, +2, +3, and the opposite direction is going to be -1, -2, -3, okay? And I want a 95% confidence interval. So I'm really looking for this number that's down here and this number that's right here, right? So that I can say, I think that the true population proportion is 61%, but I am 95% confident that the truth is somewhere kind of close. Remember, we're rounding approximately between 59% and 63%. Okay, this is my low and this is my high. And this is called the lower bound, and this is called the upper bound. This distance describes the confidence interval, and half of that distance is the margin of error. See how 2 margin of errors make a confidence interval. Okay, so I need to know, well, I can multiply this by 2. Oh, wait, 2 is just an estimation. I need something that's a little bit more precise. So in order to get the precise number for 95 without rounding, you can just look it up in a table, and I will provide those tables for you. One of the places that you can look is on this table that I'm going to show you right now. I can go back here and I can go here, and for 95% confidence interval, we're, instead of using 2, right? Remember, 2 is an estimation. They rounded, what it really is 1.96. They just round it for 2. So instead of this distance being 2, it's really 1.96. It's not really 2. It's actually 1.96 in the positive direction and 1.96 in the negative direction. All right. So what am I going to do? I've got, go back to black. I've got 0.61% here. 0.61, not 0.61. Yeah, 0.61. And I need to know the upper bound, and I need to know the lower bound. My margin of error says that I've got my standard error, and I'm going to get a little bit more precise with that. Instead of just using 0.01, I'm going to go ahead and put 0.0125. It's my standard error multiplied by the actual number of my confidence interval, 1.96. That's the 95% multiplier. Okay, so that if I multiply 0.125 times 1.96, it will give me the number, the raw score that corresponds with this. So if I multiply these two numbers together and add it to that center number, it will give me this corresponding raw score. The same thing's going to happen on the other side. I'm going to take the standard error, 0.0125, multiply it by the actual z-score that matches 95%, which is 1.96. Okay, I'm going to calculate that to get my margin of error. And then I'm going to subtract whatever this number is from 61. Notice that this and this is identical. They're the same. Just like I calculated these raw scores by adding 0.01 and adding 0.01 and then subtracting it on this side, subtracting 0.01, subtracting 0.01, I'm doing the same thing here, but I'm increasing precision a lot. Why? Because I did not round my standard error. And instead of just using this approximated 2, I actually used the right multiplier, which is 1.96. Now you might say, well, why is this changing? Well, what we like to do when we're teaching stats is we just like to kind of keep it more simple at the beginning and then kind of complicated later. But I think you can appreciate at least how that small piece of rounding is now helping you become more precise and therefore getting you closer to the truth. So let's multiply what this is. So the margin of error is going to be, and see, I still have the unrounded one here, but I'm going to just, for the sake of less cumbersome, okay, so I'm going to take 0.0125 times 1.96, and I get 0.0245. That is my margin of error. Put this in pink. MOE equals 0.0245. Now, is this going to be the same on this side? Yes, because on this side, if you notice, I'm going to have 0.0125 times 1.96. 0.0125 times 1.96. It's going to be the same. They are symmetrical. On this side, I'm going to add my margin of error to my sample proportion. And on this side, I'm going to subtract my margin of error from my sample proportion. And I'm going to end up with two numbers. So this side is adding, this side is subtracting. So let's see what I'm going to get. Okay, here's my margin of error. On this side, I'm just going to add it, 0.61 equals. I'm going to get 0.6345. And on the other side, I'm going to subtract it, 0.61 minus 0.0245 equals, and I'm going to get 0.5855. So this is equivalent to 63.45%, and this is equivalent to 58.55%. What does this tell me? It says, according to this sample, we believe that the true population proportion of Americans that are in favor of birth control being paid for by their provider, health insurance provider, is 61%. That is what we believe the proportion to be. However, we can say with 95% certainty that the true population proportion exists between 58.55% and 63.45%. Okay? We think it's 61%. Not sure, right? There's error. But we can say with 95% certainty that if it's not 61, it's somewhere in between here. It's between 58.55% and 63.45%. I have the worked out versions of this same problem on the Google Slides, along with information about the multipliers. So these are the confidence levels right here, and these are the multipliers. I also have a table in the description box below that has commonly used multipliers. These are more precise z-values, right, z-scores for calculating confidence intervals. We use them because we're trying to minimize error and increase the confidence. So this is just one way that we can minimize error by increasing precision. This is a long video, so I want you to know that the next video that I will have on here, I will have more practice with confidence levels and calculating margins of error and going through the whole process for you. So what's the big idea? Today's big idea is that since the sample is smaller than a population, there will always be errors in the calculations. Confidence intervals allow us to establish a lower bound and an upper bound within which the true population can exist. The level of confidence is related to the width of the confidence level. The wider the confidence level, the more confident you can be that the true population exists within that range. The smaller the width of the confidence level, the less confidence you should have that the true population exists within that range. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay? This is your teacher, Taurus, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!